Today we want to talk about how you pick the right kind of antenna. And we've done some other webinars before about how you aim it, things like that, and they're on our YouTube page, or you can link to them at the bottom of rfnu.com. But we wanted to talk a little bit today about antennas, um, their uh, their directivity and their gain. Um, so I guess first we have to say what an antenna is, and what it is, it's a transducer. Just like your microphone is a transducer, your speaker is a transducer. A transducer is something that converts one form of energy to another form. So with an antenna, we are converting electromagnetic waves to an electric signal that goes down into your radio, and that's how it works, as opposed to your microphone's converting sound waves into electricity and your speakers converting electricity into sound waves. An antenna is just the device that does the conversion from electromagnetic waves, radio waves, um, to electric. So that's pretty darn simple. So in looking at antennas and choosing an antenna for the job, for the venue that you're doing, I think these are the three most um, the three biggest questions that you need to ask yourself. You need to determine what it is you want to cover out of that area, and at the same time, so when you're figuring out what you want to cover, you should also be figuring out what you don't want to cover. What you don't want to cover is everything else that isn't what you do want to cover, right? Um, you need to understand how close you're going to be with your transmitter to the antenna. That's going to make a big difference. And you're going to have to consider um, how much interference rejection you want. And of course, you always want, as you can't have too much. I mean, I don't think you want to exclude your antenna from picking up as much garbage as you can, because that's eventually going to deteriorate your signal to noise ratio, your carrier to noise ratio, your dynamic range. And that's really, if you've seen any of any of our presentations at RF Venue, that's what we stress. That's the number one most important thing, that you need to get a signal 20 dB above your noise floor, pretty much, to ensure that your receiver locks to that signal and doesn't have to try to choose between a whole bunch of other signals. So let's see what we got here. So basically, for wireless mics, they're going to fall into these categories. Yeah, there's some specialty stuff outside of this, but I don't know, 99 point something percent. You're probably going to be looking at one of these styles of antennas. So you got the little whip antennas. They could be quarter wave, or they could be dipole half wave antennas. Um, it's very difficult to tell by looking at it because you can't see what's underneath the plastic, but that's the simplest form. That kind of an antenna ends up being omnidirectional in the horizontal plane. When we talk about directionality in antennas, we're almost always concerned only with the horizontal um, dispersion, right? Because I mean, we're usually not capturing people, falling from the air. I guess if you had to get a skydiver, well, we'd be talking about something else. But your audience and your stage, everything we do pretty much is horizontal. So when we talk about coverage angles, we're pretty much always talking horizontal. Then you have the LPDA, or paddle type antennas. That's log periodic antenna. And what that is, that's an array of antennas. If you look at that one, you can see there's some stripes on it. Those are antennas tuned to specific frequencies. Um, their distance apart according to wavelength matters and stuff, so that they they are constructive in the way that they are handling the signals coming through it. And with that, you get a directional antenna, normally about 120 degrees wide. And then there's helical style antennas. Helical style antennas, well, the whips and the paddles are linear antennas, right? So the waveforms they deal with are pretty much a straight line. Um, if you mount your antennas this way, we'll call that vertical. The electrical portion of the electromagnetic wave is also vertical. And that means you need to line up your receiving antenna in the same plane so that you get maximum transfer, right? You want your antennas to be polarized. And we have lots of information online about antenna polarization and stuff. We've covered that a bunch of times. The helical antenna, as you can see, is a corkscrew, right? The antenna inside your whip is a straight, more or less a straight line, a straight conductor. A helical antenna, you can see that corkscrew. And of course, that's all, it has to be exactly the way it is to be the frequencies we need it to be. The spacing and the tube size and all that stuff is very critical. But what happens with that antenna is it's spinning the pattern. It's not just a line coming out, it's spinning the pattern in 360 degrees. So that means that at any time, your receiving antenna is always polarized with this antenna. It's unique. And so we basically use that kind of antenna mainly for IEM transmission. I should mention, because it comes up sometimes, people ask me, but antennas are reciprocal. You can transmit or you can receive with any of these antennas. There's a way to do it at the same time, but it's enormously expensive, takes a bunch of electronics. Just, if you have a NASA budget, you could talk about it, but basically you can do one at a time. And then, of course, if your antenna is amplified, if you have a little amplifier on your antenna, you can't. It becomes a receiving antenna only. So these are the main styles that you're going to deal with. And these are kind of generally the patterns. So if we're looking at the red areas here, this is, if you were looking top down, this would be your coverage, right? So an omnidirectional whip antenna basically is in the horizontal is going equally or nearly equally in every direction. These aren't perfect, but it's close enough. We'll just call it equal in every direction. Your paddle antenna is directional, and basically they're almost always the same. So we're taking that circle and we're cutting it into 3 pie pieces. And we're only going to look at 1 pie piece and we're going to ignore the other 2 pie pieces, more or less. We're going to have very low coverage in the 2 pie pieces that are essentially behind us. Okay. Helical antennas are much more focused as a general rule. So where your paddle antennas generally are going to be about 120 degrees, which is really interesting. 120 degrees is sort of the average peripheral, how do I do it? Peripheral vision that humans have. So which is really good. If you're using a paddle antenna, if you put your head, if you're going to put your paddle antenna on the wall, if you put your head on the wall, you're covering what you can see. And what you can't see is greatly reduced coverage. Realize they don't stop. We don't have hard borders, right? They fade out. They get much lower in their ability to receive when you get outside that triangle. But there's always coverage. And actually, pretty much all antennas, if you get very close to them, really don't have any pattern at all. You have to get a little distance for the pattern to really behave. Much like you're probably used to omnidirectional microphones and cardioid microphones, right? This would be to the left. Your whip would be like an omnidirectional microphone. Your center would be like a cardioid microphone, and then your helical antenna would be like a super cardioid or maybe even a shotgun mic, very narrow in its coverage. So helical antennas generally are about half the coverage angle of a paddle, right? So that it's just about picking the right antenna for the job. You can't say, well, one antenna is going to be better than another without knowing a whole bunch of other things that you have to do. We're always dealing with systems. So all the, your where your transmitter is and how far away and what cables you're running and what microphones, wireless mics you're using and how much transmit power they have and your antenna, all these things work together to give you an answer. So you can't look at any one thing and get a very good answer. It can start to lean you in that direction, but it's not really going to give you an answer. You have to look at all the pieces together, right? We can talk about how many horsepower your engine has, but if you don't have any tires on your wheels, your car's not going to go very far. And we're interested in driving cars. We don't really care how much horsepower the engine has. That's a factor going into other things. So it's kind of like that. You kind of got to put all these pieces together. Um, so what do we need to cover? Um, and this is really important because we want to cover only what we want to cover. Everything else, if we cover areas where we're never going to have a transmitter, almost for certain that area is going to have some amount of noise, RF noise in it we're trying to avoid that. So, in a perfect world, I guess maybe someday somebody will invent, laser point antennas that only hit your transmitter and avoid everything else in the world. And wouldn't that be wonderful? But we're not quite there yet for anything that, unless you have a NASA budget, they can probably do it today. But it's not really going to show up in our world. So it's important that we cover what we want to. So I get questions all the time. I'll get an Omni antenna and cover everything. Well, if you need to cover everything, that's the right antenna. But most times we're looking at a defined area where our transmitters are going to be. Like they're going to be on a stage, right? Now, if you got people running around everywhere or you're doing, theater in the round or something, well, then that's everywhere. But that's the same way. People will tell me um, they've got a building and they want coverage everywhere in the building. And I'm going, well, do you want coverage in the men's room? You want coverage in the kitchen? You want coverage in the broom closets? Because that's part of everything. Nobody does, or at least not very many people do. So you have to really understand where you're trying to pick up your transmitters from. And you would like to match your antennas as closely as you can to pick up that area and nothing else. You'll never get exactly there. So this is kind of, again, what it would look like if your antenna was placed where that little arrow is, and you had an Omni antenna, it's going out equally in all directions. If you have a paddle LPDA antenna, it roughly goes out in 120-degree coverage. And if you have a helical antenna, they're typically like 70 to about 40 degrees. So they become much more focused, which has benefits and problems that we'll talk about, I guess, next. So again, it's like, what are you trying to cover? If I'm trying to cover only the end zone of this football field, then that helical antenna placed at the opposite end zone, that would be probably something I'd choose. If I was trying to cover the entire field, I should point out, just to scale this, to get this to all fit on a slide where it makes any sense when you look at it. I'm not suggesting that the coverage stops at the end of these triangles, right? That green is going to continue on. And actually, it's going to continue on to infinity, hundreds of millions of miles. Antennas antennas have no distance limit. Uh, well, until we start talking in light years, I don't know what happens. Even then, I don't think it does. But they have no distance limit. They will pick up for forever. But the signal gets weaker and weaker and weaker as you get away from it, just like your loudspeaker does, inverse square, right? So it's the same principle. It gets weaker and weaker and weaker, which means the signal is falling down into the noise. And about 20 dB is where wireless microphones that we use can extract that signal with an extreme high reliability level. It'll work a little lower than that, but then you'll start getting dropouts and little funny things. So that green doesn't stop there. It goes 100 miles, 100 million miles in that direction. The red, the paddle spreads out a bit wider. And I'm also going to cover the whole field, but I'm also going to cover the sidelines and maybe part of the stand. So maybe I got announcers out there that I want to pick up. Where with the green one, I can kind of exclude what might be happening on the sidelines. You might want to do that depending on what's there. If there was TV broadcasters with a bunch of wireless, who knows what, and all their radios are interlacing with yours and interfering with yours, so you might want to exclude them. The red, you're going to pick them up. The Omni, and again, I'm not saying it stops where that circle is. It continues to spread forever, getting weaker and weaker and weaker as you get further away from the center of it. But what's happening with that Omni, if I put it at that position, is I'm also getting all the people tailgating out in the parking lot. Now, if I'm trying to pick them up, that's what I want to use. But to my way of thinking, I'm probably not. And that way, if I'm not picking them up, I'm not picking up any interference that they might be creating. Now, for the purpose of this discussion, we'll consider that interference is equal in all directions. And of course it's not, because if I have a television transmitter sitting at 11 o'clock up here, obviously I really got a lot of noise coming from up there. So if you have something, this might happen. I did a presentation room, a little mini theater, held about 500 people, got a big stage and everything. But in one corner of their room was the electrical service into the building, all the transformers and all the three-phase, all the huge amount of power was coming into this room. And it's like, boy, I don't want my antennas to pick up any of that, because that garbage is much stronger in the direction of that than in the other direction. But, so sometimes you'll see those things. If you had to deal with an installation, maybe in like a manufacturing plant, someplace where there's all kinds of heavy duty machinery, because who knows what might be coming out of that, or a casino. I mean, slot machines are screwy. I mean, they put out who knows what kind of garbage. And if you got 600 slot machines coming at you from all over the place. But if all the slot machines are on one side, then you can use a directional antenna and point away from them. Okay, I'm getting kind of deep in the weeds. So again, with the triangles, we're only picking up that area. We're ignoring everything else. But in that Omni is picking up everything in the gray area. And again, if that were an Omni and I put it there and I had a stage, that means I'm picking up all the noise and stuff. I'm picking up everybody in the audience with a T-Mobile cell phone. I'm picking up just everything coming from every direction. And if I'm not looking to pick up a wireless mic transmitter in one of those spots, well, then that's not the antenna for that job, right? So the idea that, I'll just pick up anything is, I would suggest that you or your clients, drill down just a little bit into what it is they really want to pick up. I mean, we can do it either way. but it's more expensive to pick up everything. Again, if I've got to pick up the men's room and the kitchen, I can do that. It's easy enough to do, but they don't really want to do it, and they probably don't want to pay for you to put that in and then never use it, right? So you kind of got to work with them a little bit. And really, the more you can define, the narrower you can create the scope of what you need to do, the easier it is to do it well. So I'll leave you with that part. I do want to, obviously here we're only talking about a single antenna. If we're doing wireless microphones, we need two antennas. We need an A and a B so that we get diversity. And one of the things people think about doing is if I've got a big space like this, a basketball court, a football field, whatever, I'm just using a rectangle this size because it fits nicely on the screen. If you put one antenna on the north side facing south and one on the south side facing north, you'll get extended coverage, but you will have diminished diversity. This is by no means to scale. This depends on a million things, but I wanted to do it this way just so you understand the concept. This isn't wrong. It's just what it is. If you get right down close to one of these antennas, and you've got the distance of a football field between these, and you get really close, 10 feet from one of these antennas, you're so far away from the other antenna that you may not have any diversity. So if that antenna goes bad, the signal drops in that one antenna, you may or may not have anything left to switch to. So I get this. This is it's a very common thought. I'll just spread the antennas all over the place. And it does get you coverage, but it doesn't get you diversity coverage. So just kind of keep that in mind. There may be a time when that's the best answer, but generally speaking, it's probably not. Um, so uh, we need to talk about distance from transmitter to antenna. Um, we want we want to pick up a strong signal. We want to pick up the transmitter um, as strong as we can with the receiver. Now, we're talking about wireless microphones. If we were talking about IEMs, it's exactly the same, but it's backwards. Okay, they're just radios. They work exactly the same way, but we're just going the other direction. I guess the easiest way to say that. We want to pick a nice strong signal up because the stronger we can pick up the signal, the noise is essentially going to be, let's call it fixed. It's not really, but it's sort of it's should be constant, and there's an amount of noise, right? So if I get my transmitter closer to my antenna, then the signal is going to be stronger and the noise is going to be the same whether I'm close or far. We're going to look at it that way, right? So if I'm trying to speak to you, from 20 feet away, and you can hear me, that's fine. But if somebody's, if we're outside on the grass and somebody has a lawnmower going at the same time, you may not be able to hear me at 20 feet. But if I walk up closer to you, equivalent acoustic distance, I get closer to you. I don't have to speak any louder, but you'll hear me because the signal to noise ratio is better. So we'd like to get as strong a signal in the antenna as we can while picking up the minimum amount of noise. So what we want to do is we don't want to use an antenna that's really any stronger or not much stronger than we need, right? An antenna that'll go for 10 miles if you're only trying to pick up somebody at 50 feet is not a benefit because it's picking up 10 miles less 50 feet of extra noise, and that noise floor is coming up, and we don't want that to happen. So if you're going to be reasonably close to your transmitter, to your antennas, you're better off using lower gain antennas. And if you're going to be far away, then you want to use higher gain antennas, right? So that kind of breaks down kind of like this. So lower gains are going to be your omnidirectional antennas. So we should talk about antenna gain. Antenna gain, you'll see that it's not like amplifier gain, right? Where you have a circuit that actually amplifies your signal. What happens with antennas is because of focus, they can more concentrate the area, right? So it's kind of like using a megaphone, right? We concentrate the sound. When you're listening to people talking, um, they could turn their back to you. You can still hear them from, their mouth doesn't really focus the sound in a narrow, straight path. It spreads. I can hear people if I stand reasonably close to them, behind them. I can hear them better from the front, but it goes all the way around. So, but if I concentrate that sound using a megaphone, what I'm doing is I'm taking some of that sound energy that would have gone where I don't want it to go, in this case behind me, and I'm going to squeeze it into the space that's going forward, and that's going to create higher density of energy in that direction, right? So if you look at gain figures for antennas, that's what it is. It's not an amplifier. We look at it in dB, um, from a mythical, what they call an isotropic perfect sphere antenna that doesn't really exist. But we look at that as a model, and then we say, well, how are we slicing that pie? Actually, going to be a wedge. How are we slicing that wedge up? And then so we're concentrating that energy, and that's what we call the gain of these antennas. But it is important. So your lower gain antennas are your omnidirectional antennas because they don't really concentrate the area very much. I should say that we call them omnidirectional. They're really not omnidirectional. They're omnidirectional in the horizontal plane. They're really toroidal. They're sort of a donut shape. And so if you use that little whip antenna, it has lower pickup directly underneath it and directly above it. But you probably don't have anybody above it. And unless you've mounted it on the ceiling and pointed it straight down, which I see people do, in that case, straight down isn't going to have as much pickup. Of course, you're closer to it again, so all these things kind of average out. But just be aware of that. At the bottom there, that's our diversity series antennas, and our diversity omnidirectional antenna is almost a perfect sphere. In other words, it doesn't make any difference to that antenna which way you twist it, because the pickup pattern is actually a ball, not just a donut. So that one you can point it down, you can point it sideways. It really won't make any difference at all. I should mention, because people do ask me, like with your diversity fin, can I mount that upside down? Yes. I mean, as long as it's that same, if you just flip it over, it's the same, essentially. So yeah, no problem doing that. Anyway, we get to medium gain antennas. That would be your paddles. Generally have, 5 or 6 dB of gain compared to that perfect antenna that doesn't exist. Um, we have two diversity antennas. The diversity architectural antenna, the white square, is a little lower gain than the diversity fin antenna. So you're going to get an antenna that's probably good with the architectural antenna. Roughly you could probably cover, a room 200 feet by 200 feet if you had to. Where with the diversity fin antenna, the black one, that might be like 300 feet by 300 feet. It depends exactly where you are, but that's kind of generally what I would expect without thinking about it too much and without, actually calculating it all out. And then you have your high gain antennas. So these are going to be your helical antennas, our CP beam. I should have put, we have a CP architectural that has less gain than that CP beam. Um, and so if you're going to be closer to it, so it's a really good antenna. If you're going to put your antennas, if you've got like uh, a nightclub or a church maybe that, not a huge mega church, but a church that holds, four, five, 600 people maybe, and you're going to mount the antennas on the sidewall, and all you need to do is cover the stage. That's going to be a benefit because one thing I should mention is that you can get too close to an antenna. So again, just like if we're speaking to each other across the room, that's fine. If I get up and walk myself to a quarter of an inch away from your ear and I speak at the same level I was speaking when I was sitting 6 or 8 or 12 feet away from you, you would now tell me I'm screaming in your ear. I'm speaking at the same level, but the intensity is so much more because there's no loss for distance. So the same kind of thing happens with antennas. If you get right up to an antenna, if you take your handheld microphone, you hold it right up to that D fin, it's going to be so strong that it's going to overload the front end of your radios. And this is a problem, especially for people that use amplified antennas. That's just not a good thing. Amplified antennas is really something that should almost always be avoided. They're right. Sometimes if you're very close to your antenna and you have this huge distance to try to run, but they don't, there's better ways to do it that don't cause as many problems. So you want to think a little bit about gain. You don't want, um, I guess it's intuitive to kind of say, well, I want the biggest, most powerful one that I can get because it certainly will cover me at a close distance. I won't have to worry about fade out. Well, yeah, but it covers you way too well. So, an antenna, uh, if were to use that CP beam for wireless microphones, of course, you need to use two. That's not a diversity antenna. But now you're talking about where your diversity fin might do 300 feet, your CP beam might do 600 feet. Um, and all these numbers I'm throwing out could easily be double that in the right situation. And, in the middle of Times Square, they'll be somewhat less than that, but you just kind of use those as general figures. So, so when you're choosing your antenna, you got to remember that your antennas require line of sight, right? If your transmitter can't see your antenna, then you're got your fingers crossed that enough random bounces off all the walls, all the multipath is going to go around your obstacle, and get to your antenna. And it might. Uh, if you're really good at picking lotto numbers, maybe that you're all right, but I'm not. They just take my money, never comes back. Um, so you want to try to match the pattern with the job. I mean, pick an if I just need to pick up this area, pick up that area with a directional antenna, and if I need to pick up everything coming at me from every direction, I might want to pick an Omni. So that's it. I get asked all the time, how do I aim my antennas? And I really think most people that ask me that would know how to aim their microphones, that transducer. It's the same thing. You need to point it at what's making the noise, right? If you want a microphone to pick up something. And it's the same way. I mean, you point your antenna at the transmitters that you have. And we have a webinar with, if you want to get into all kinds of situations for antenna placement, there's a 45-minute webinar that covers lots and lots and lots of different examples. But it's really that simple, point it at the transmitter. Now, that could be difficult if you've got transmitters all over the place. You have to consider that. But that's what you're doing. You're pointing the antenna at the transmitter. You don't want to cover anything more than you need to, because inevitably you're adding noise, and that noise will catch up with you someday, somewhere, and that's your noise floor. Your noise floor is rising up. Your signal is going to be what it's going to be, based on how strong it is coming out of your microphone and how close you are to your antenna and how much gain your antenna has. That all that stuff is going to be what it's going to be. But if you're covering area that you don't need to cover, you're inevitably adding more and more and more noise, and so that noise floor is coming up at you. And when you don't have about 20 dB left, is when you start to have problems. And then if you have a situation where you do have obstacles, walls, if I've got to pick up 4 classrooms, well, don't count on the antennas going through the walls. I mean, they do to some extent. You might get lucky. It might work. In some places, it'll work. In some places, it won't work. But I would never design a system uh, to have me think that I'm going to get coverage through a wall, because it depends on the materials. It depends on a lot of things, but you're definitely losing signal. So if you need to do that, we make a multi-zone, a 4-zone combiner where you use multiple antennas. I mean, your best bet really is every enclosed space should have an A and a B antenna. That's the best way to do it. You don't always have to do it that way, but that would be the best way to do it. Excuse me. So I hope that gives you a little help in picking stuff. And I think we got some time left over here, Adam. We did get a bunch of questions, and let me know what we got.
Yeah, absolutely. I can pick and choose here. I don't see anyone's asked questions so far. So if you do have questions on what Don's presented, please enter them in the Q&A and I can call them out. I'm also going to launch a poll here just to tell how many of you have attended webinars, RFNU webinars in the past. So I'm going to go ahead and launch that. So just take a second and I'll pick some questions for you, Don.
Yeah, if you fill in this little questionnaire, we appreciate it because um, otherwise, I keep repeating myself and repeating myself. But if it's new to you, if you've never heard it before, that's what we're kind of trying to figure out here. And it looks like we're kind of equally divided um, uh, for everybody, and that's fine. Um, it's no problem. And sometimes hearing it more than once or twice, it takes more than once or twice or 3 times. Some of these webinars, have an awful lot of points being made, and trying to remember them all. I don't walk out of webinars remembering 100% of what was there. So we do repeat it, and sometimes that brings a little additional clarity.
Excellent. So it looks like everybody has filled out the poll. Thank you for that. And I want to just make a comment too. If you want to see any of the previous webinars that Don has done, I know he said one of them, you can go to our website under resources and find a webinar page where we post all these on a landing page. So you can, go back in a couple of days from now and see this one posted and get all the webinars. So get your coffee ready. There's a lot of material on there. I'll go ahead and share the results so everybody can see. Can you guys see that? All right. Cool.
So we would like to thank the people that keep coming back, of course. And if this is your first time, I hope you got something out of this. And we do these once a month. We send out a notice that we're going to have it. We ask you to register just so we get an idea how many people are coming. And we also ask you to submit a question at that point, although it looks like we've got some new here. So
Yep, they're coming in now, so I'll start with those. So are there things I need to think about combining different antennas made by different manufacturers?
well, so you can mismatch stuff forever, and that's not a problem. It is what it is, right? So if I'm using an A and a B antenna, and this one's got a lot of gain and this one doesn't have much gain, that's okay. And that may work in some situations. That may be exactly what you need. So there's nothing preventing you from doing that. Assuming that your antennas are the right frequency for the job that you're doing. And honestly, that's pretty hard to screw up in the United States because the FCC is so regulates everything that can be sold. You don't have to worry about mixing brands. You don't have to have people ask me, do I have to have the same? I got one antenna here and one there, but one's a short cable, one runs a long cable run. Do I need to coil up 20 extra feet of cable? No, just use a shorter cable. That signal will be a little stronger, and your system will react with what you would expect to happen when one antenna is a little stronger than the other, but it's not a problem by itself. So uh, combining antennas, I mean, there you need to use the proper tool that combines them, if that's what you really mean when you said combine. You do need to use um, splitter combiners. You cannot use BNCTs, that just hardwire all that stuff together. They just don't work at the frequencies we're working with. That was kind of, I mean, it was never great, but it was kind of okay for old school VHF TV. Much lower frequencies aren't nearly as affected. But so if you're using the proper thing to combine your antennas, yes, you can.
Great. All right, the next one. Would I need two of RF venue Omni antennas for good diversity?
Well, no, because a single physical package is two antennas. So that's always that's always a little. I always have to stop and explain that. So our diversity, our Omni is a diversity antenna. Um, I take that back. We do have a little kit with little whips for little mini stuff, but basically, if you're using our diversity antenna, no, that is two antennas. So it's a single package. You're going to connect two coax cables to it and treat it as two antennas.
Cool. This is one of my favorites. When using two LPDA antennas, is it best to angle them 90 degrees vertically from one another to avoid cross-polarization fade?
It assists, generally speaking, in that. Okay. It doesn't correct it. So if you had, so when they're 90 degrees apart, we could be talking about one vertical and one horizontal, and 90 degrees is just, it doesn't matter. Your polarization is between 0 and 90. So as long as you're doing that, it will double your chances in not having a cross polarization fade, but it won't eliminate it. Because you have two antennas separated by space, so they're not seeing the same radio wave. They're seeing two different radio waves, and each one of those radio waves could drop out by itself. Our diversity series antennas, because they're co-located at a single point in space, they only see one radio wave, so they're only judging the polarity. They don't have to, you don't have to account for phase differences between the two because of distance.
Great. Here's an interesting one. Overhead position of architectural Omni, it's still directional, and the wider beam CP antenna. Effective problems looking at center stage overhead.
Well, you have to work out the geometry. So when you mount an antenna overhead, you have to consider what the pattern is and what that is going to project like down on your floor or 4 feet up from your floor, right? So just imagine if your antenna is fairly directional, then you've got a spotlight. And you're going to create a little round beam on the stage, or if it's a floodlight, you're going to cover more of the stage. So it's going to depend on your ceiling height, how far it spreads out. So if you have a theater with a 30-foot proscenium and a 50, 60-foot stage, that's probably not a problem. If you're trying to put it in a boardroom that has a 9-foot ceiling, you're going to have a smaller coverage area. Now, that could be a very good thing because if all I want to do is pick up the conference table in the middle of the room and I don't have to deal with a wall full of computers and stuff they've got someplace else because all that's making noise, that might be a very good way to do it. But you just consider the pattern. In the case of our what did they say, CP arc, that's a conical pattern. So roughly it spreads out about 3 feet in radius for every foot of ceiling height. So you can, like I said, sometimes you want to use an antenna to exclude. And so if that's what you're trying to do, then that could be a very good way to do it.
Cool. How are Omni antennas constructed that are made for full frequency spectrum?
How are they constructed? Well, in the simplest form, it's just a straight piece of wire, right? And the length depends on the wavelength, the frequency that it's going to be most sensitive to. That would be a quarter wave antenna. And then there's a ground reference that's why it has to be bolted to your receiver. A dipole whip is basically just two of those little pieces of wire. Um, and that way it doesn't have to be mounted to the chassis. If you look at an LPDA antenna, really what you're looking at, you can see those stripes. You're looking at a whole bunch of little Omni quarter wave antennas that are put together in an array. And so they are, carefully calculated to work together. Um, and 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 they kind of tend to pick up higher frequencies at the short end of them and longer frequencies at the back end. And depending on the space, and there's isolators between them, it creates an array. Like when you stack speakers together to make a line array. If you just throw a bunch of speakers together, you get something. You get some kind of pattern control, but probably not what you expect. And as you calculate that all out, you can you can you can more focus that. But yeah, I mean, basically, antennas are just whips. That helical antenna is just a straight piece of wire, but the way it's twisted and the spacing between it and the diameter and all that stuff, it all adds up. We're dealing with wavelengths, right? So we're dealing with electromagnetic waves, and we're interested in certain frequencies, and those frequencies have a spacing. And so we have to pay attention to that spacing as the wave goes, it creates a sine wave. We have to look at the wavelengths.
Got it. So, for a theater application with both antennas located at the front of house and the back of the house, are there situations where using two antennas of different type makes sense to get better diversity, aka an LPDA and an omni dipole?
Well, I sub I would so to make it simple as a general rule, no. I would have to really think about that. I mean, there's maybe some place in the world where that might be a good idea. Uh, then again, you can look at our diversity fin antenna and you go, well, wait a minute, you got one paddle and you've got a dipole out of whips. What's up with that? But it's turned sideways. They're different in gain, so the way that it switches between A and B, all that stuff is very carefully worked out. So while it may look that way at first glance, there's a reason for it. I would think just having two different kind of antennas like that. Again, it's going to give you coverage, but you're going to probably not have consistent diversity. So, I mean, if your polarization didn't change, you'd really have no reason to worry about it, right? But the trouble with handheld microphones, people are moving them, or belt packs, your actors are bending and moving and stuff. It they're not fixed. If you were going to put your transmitter, your handheld transmitter on a mic stand, and all you were going to do was move the mic stand around so that the orientation never changed the relationship to your antenna. I hope I'm not this is getting too deep. That would be okay, but that's not the way we use them. So no, I wouldn't. I That would be an extremely rare situation where that would be good, I think.
Got it. So last one for the live questions, and then we'll start going with the submitted questions here. How far away can I mount my antennas, like in a catwalk or backstage, from my combiner before I start having issues? Can I amplify the signal, or is that a bad idea?
So the answer to that is go to our website and use our performance calculator because it depends. I get that question. How long can I run my cable? How far will my antenna go? I get those kind of questions. that's part of a system. So you have to look at all the pieces together. So if you go to our website, top of every page, there's a round button that says Performance Tools. Click on that. Use the one that says Check Your System's Performance. And what we have to know is we have to know the strength of your transmitter, the strength of your antennas, how far your transmitter is going to be from your antenna, how long your coax runs are going to be, some other couple of other things. And we look at those all together and we see that we see how strong the signal is going to be by the time it gets all the way to the other end. You have to remember, if you have a good enough signal, you can do all kinds of crazy wrong things and it won't matter. You have well enough, but don't count on it. You got to get lucky if you're if you're working like that, you know. And it depends where you're working. If you're working in a metro area, your chances are extremely diminished compared to, working out in the middle of a cornfield in Indiana, where there's nothing around and no interference. So that's the qualifier is what the interference level is going to be compared to what we can calculate.
All right, we got some time for a few more that we've hand selected from your submissions. Thanks for the questions. Are RF venue antennas completely interchangeable with Shure antennas?
Yes.
All right.
Yeah, so you have to think about this. What we're dealing with, what Shure antennas are dealing with, and everybody else's coax, and everybody else's distros, we're dealing with electromagnetic radio waves that are a universal force of nature. These aren't proprietary things. Now, what your Shure microphone, how it codes the signal that it sends, our antennas are only care about moving the signal, the coding of the signal, whether what language you're sending it in. You're sending it in English and or Spanish or German or Latin or whatever. That depends. You've got to be able to understand it at the other end. It's just like a PA system, right? I can put a microphone up there, and if somebody gets up and speaks English and you understand English and you're sitting in the crowd, you get it. If the next guy gets up there and speaks a language you don't understand, the PA system still works perfectly. It's your inability to understand his language. And so that's the same thing. That's why we can mix and match all this stuff. The radio wave is universal. So it's an analog signal and it's universal. So that you can mix and match stuff, no problem.
Cool. Should bandpass filters always be used on RF mic antennas, or are there certain situations where it makes more sense to use them?
Well, they almost, you can't ever say anything's absolute. They almost never can hurt you. Um, what they're going to do is they're going to block things outside of the frequencies that you're interested in, so those outside frequencies don't mix with what you're doing and make it much harder for your radio. So the simple question is no, they're not going to cause you any problem. I mean, I could probably work up some specific thing, but no, in the real world, no, we're good.
Cool. So this is a lot of the same question you guys asked. So I think Don will be able to cover this in one question. What are the considerations on deciding the separation between locations of IEM and wireless mic antennas?
Well, all antennas need a little isolation from each other because when the antenna itself, when it's receiving a signal, is becoming an electromagnet, right? When you put a current through a conductor, it creates magnetism. And so if your antennas are too close together, the magnetism jumps from one into the other antenna a little bit to greatly simplify what's happening. And that jump becomes noise in the other antenna that you're shooting down the system. So in big rules of thumb, we'd like to see it about 3 wavelengths or a little more apart. And with the wireless mics we're talking about in the USA, 470 to 608, a wavelength is roughly 2 feet. So we'd like to see them 6 feet apart from each other to mostly knock out any crosstalk, right? That pretty well does it. You have to have antennas, uh, unless they're co-located. You have to have them at least about 6.5 inches apart for diversity to happen. You have to have a quarter of a wavelength, so quarter of that 2 feet, um, for your before your radio can tell a difference between two antennas. Uh, but at 6 inches apart, if you just put them on the back of a single receiver, they're interfering with each other. Now that won't knock you off the air just by itself, but that's adding more straws onto the camel's back. Remember, what we're trying to hit is that 20 dB, and that's lessening that. Of course, if you're starting with 40, you can lessen it quite a bit. But and we'd like to see remote antennas, whether they're whether they're for mics or ears, about 6 feet apart from each other would be a pretty good way to do it, almost always.
Excellent. This is a favorite of mine because I don't know if it's completely well understood by everybody. Can external passive antennas be run for a single wireless unit to combat dropouts, or do you need a splitter?
Oh yeah, I get people that ask me, do I have to have a combiner or do I have to have a distro or no, it's just an antenna. You can plug one diversity fin into one receiver. That's all you've got. You will have greatly improved the reliability of that single radio, but no, you don't have to have anything else. It's just two antennas. And antennas are, what they are. So yeah, you plug straight in.
Great. All right, two more questions, guys, and that's all we have time for. This is a good one. How to find frequencies in my area?
Okay. Uh, if your area is the United States, again, if you go to our webpage and click on that performance tool button, the other program it would take you to says build your system. And so what that program will ask where you are. You give it the address of your venue, and then it will ask what wireless mics or ears or both you are using. And so you have to say, I have this many Shure in this block, and I have this many Sennheiser in this block, and this many Audio Technica in this block. Um, it then takes you to another screen. If you're interested in adding to that system, it's going to recommend a lot of things that will work well with what you've already got. So you don't buy something, take it out of the box, and find out, wow, this won't work with the rest of my stuff. Anyway, if you don't need any new mics, you just skip past that. And it's going to give you a frequency coordination based on your location, and based on the frequencies of your microphone. So what it's doing, it knows about certain interference that's in that area. It knows that, and it gets updated to that interference every 24 hours, which is really cool about ours. And then as it knows, so it knows what you've got, it knows what interference is there, and putting those two things together, it calculates the frequencies that if you tune to, you will minimally impact the rest of your mics and ears, right? Um, and it does that. It does that based on like I said, knowing what it knows about the location. So what it doesn't know, if you have an X-ray machine on your stage, it doesn't know that. In that case, why would you have an X-ray machine on your stage? So I mean, if you're not around crazy industrial machinery or hospital machinery or in the middle of a military airfield, it should work awfully darn good. And it will handle up to 24, 25 devices.
I believe that's
24.
correct. 25. Yep.
25. Yeah. So as long as your mics and ears don't total past 25, you can do that. Now, you can supercharge it if you have a spectrum analyzer, if you can make a measurement of what's happening in your particular venue, you can add that to it, and that will supercharge its ability to do that, because now it knows if you do have an X-ray machine on your stage.
Excellent. All right, we got time for one more, and this is a hot button topic. We got a lot of content about this topic on our site. Definitely check it out. How do I prevent frequency clash when I have a lot of mics, IEMs, and also a router for the Wi-Fi connection to the mixer?
Well, the router is, 2.4 or 5 gigs, so it's pretty far away in frequency from the standard TV band UHF. That when we talk about wireless mics, that's what we mean, unless we qualify it some other way. So those mics are working from 470 to 608 roughly. That's reasonably far away. However, all radios interfere with all other radios based on how strong they are, how close they are together, and the frequency separation. So the frequency separation is pretty good. So unless you're right next to it and it's screaming in your ear, it's probably not going to bother you much. If you're using 2.4 wireless mics, that'd be a different story. Uh, there's there are some of those that are better than others at dealing with that, but it won't bother most of your wireless mics. But don't set it right next to your, don't put it on the table right next to your DFIN. I mean, you want to separate those. Um, and so, but you don't need a whole lot of separation. 6 feet would be good. I mean, 10 feet would be better, 100 feet would be, but it's crazy. And it wouldn't be that much better. I mean, it would just be a hair better. But the more distance you have, the more isolation there is. But that should be very easily manageable. I mean, don't, well, where that could happen. Okay, well, let me back up to where that could happen, where I do see it happen. I see a rack and maybe they've got a distro, maybe they've got a combiner. So they're doing that, but they've got their antennas front mounted in the front of their distro and front mounted in the front of their combiner for their IEMs, and they've got their Wi-Fi router sitting right on top of that, going back to their mixer. Those antennas are all too close to each other. That is not a good situation. You might get away with it, but I wouldn't do that. I mean, I would think that's a disaster from day one, because you've got some things transmitting and some things receiving. And again, when they're real close together, they're screaming in each other's ears. So you want to separate. I don't very much care where the receivers are and the inner monitor transmitter is and your router is. I mean, they do leak a little bit to each other, but it's their antennas that need to be separated from each other. So you can put all that stuff in the same rack, and that's, without much problem. But you are going to have to remote some of the antennas. You got to move them away.
Awesome. Well, that's all the time we have and all the questions. We've exhausted all these questions. Great job as always, Don. A lot of useful information. We'll be posting this video to our webinar page. So take a look out for that if you wanted to rewatch it or share it. If you have any questions, you can email me, adam@rfvenue.com, or Don, D-O-N, at rfvenue.com. We're always happy to help review your projects and just provide any assistance we can. So thanks again, everybody. Look out for the next webinar next month, and we'll see you at that time.
Thanks, guys.